50 feet below the surface of the Mediterranean. A diver's light illuminates something impossible. A structure, massive, covered in barnacles and algae, but solid, intact, as strong as the day it was built. 2,000 years ago. This isn't natural rock. It's concrete, Roman concrete, built during the reign of Augustus Caesar. And it's stronger now than when the Romans poured it. Modern concrete bridges crumble after 50 years. Highway overpasses crack and require constant maintenance. Dams develop fissures. Buildings decay. But Roman harbors, submerged in corrosive seawater for 2,000 years, are still standing. The Pantheon Dome, the world's largest unreinforced concrete dome, hasn't cracked in 2 millennia. The Romans built better than we do, with ancient technology, without computers, without chemistry labs, without steel reinforcement. How? That's the secret scientists have been trying to crack for decades. And what they've discovered changes everything. Because the Romans didn't just build structures. They built material that heals itself. Before we decode the mystery, you need to understand what we're talking about. The structures that defied time. The Pantheon, built around 125 AD under Emperor Hadrian. The dome spans 43 meters, 142 feet. For comparison, that's wider than the dome of St. Peter's Basilica. But here's what's insane. It's made entirely of unreinforced concrete. No steel, no rebar, just concrete and aggregate. And it has no cracks, none. After 1,900 years, modern concrete domes that size require extensive steel reinforcement. Even then, they develop cracks within decades. Maintenance is constant. The Pantheon? Still perfect, still functional, still the world's largest unreinforced concrete dome ever built. But if the Pantheon is impressive, the harbor structures are impossible. Caesarea Maritima, a massive Roman port in what's now Israel, built by King Herod around 25 BC. The harbor structures, breakwaters, piers, foundations, were built directly in seawater. Modern engineers know this is suicide for concrete. Seawater is highly corrosive. The salt attacks concrete, penetrating it, breaking it down chemically. Chloride ions corrode steel reinforcement. Sulfates attack the cement matrix. Modern marine concrete structures require special mixtures, protective coatings, and cathodic protection systems. Even then, they last maybe 50 to 100 years before requiring major repairs. Roman marine concrete has been underwater for 2,000 years. And it's getting stronger. The list goes on. The Pont du Gard aqueduct in France, 2,000 years old, still standing, still functional. The markets of Trajan in Rome, multi-story concrete structure, largely intact. The baths of Caracalla, massive concrete vaults, still imposing after 2 millennia. Countless bridges, roads, and foundations throughout the former Roman Empire, still bearing loads, still solid. Meanwhile, modern concrete structures built in the 1950s and 60s are crumbling. Bridges are being replaced. Dams are showing dangerous deterioration. So what did the Romans know that we forgot? For centuries, the recipe for Roman concrete was lost. Medieval builders tried to replicate Roman structures and failed. Renaissance architects studied the ruins, but couldn't figure out the secret. It wasn't until the 20th century, using electron microscopes, X-ray diffraction, and advanced chemical analysis, that scientists began to understand what the Romans were doing. And it turns out, the secret was in the volcano. Roman concrete, or opus cementitium as they called it, consists of 3 basic components. 1. Lime, calcium oxide, made by burning limestone in kilns. This was the binding agent similar to modern cement. 2. Aggregate, chunks of rock, brick, or tufa, volcanic rock. This provided bulk and structure. 3. Volcanic ash. And here's where the magic happens. The Romans didn't use just any ash. They used pozzolana, volcanic ash from specific regions, particularly near Mount Vesuvius and the Campi Flegrei volcanic area near Naples. The name comes from the town of Pozzuoli, where massive deposits of this ash exist. The Romans called it pulvis pudialinus, dust of pozzolani. So what makes volcanic ash special? At the microscopic level, pozzolana is a glassy, highly reactive aluminosilicate material. When mixed with lime and water, it undergoes a chemical reaction called pozzolanic reaction. Here's what happens. Step 1, lime, calcium hydroxide, dissolves in water, creating an alkaline solution. Step 2, the volcanic ash reacts with this alkaline solution and with dissolved calcium. Step 3, new minerals crystallize, particularly calcium aluminum silicate hydrates, or CSH phases. Step 4, these crystals form an interlocking matrix, binding the aggregate together into solid concrete. This process continues for years, decades, even centuries. The concrete keeps reacting, keeps forming new crystals, keeps getting denser and stronger. It's not just setting, it's evolving. But the really wild part? The Romans discovered something by accident that modern scientists only recently confirmed. When Roman concrete is exposed to seawater, it doesn't corrode. It improves. Research led by Marie Jackson at the University of California, Berkeley, and published in American Mineralogist and Science Advances, revealed the mechanism. When seawater infiltrates Roman concrete, dissolved minerals in the water, particularly aluminum and silica, interact with the lime and volcanic ash. This triggers the formation of rare minerals. Altobermarite, an aluminum-substituted form of tobermarite, an extremely stable and durable mineral. It grows through the concrete, filling microscopic cracks and voids. Philipsite, a zeolite mineral that forms in the pores, reinforcing the structure. These minerals interlock with the existing concrete matrix, essentially healing any microcracks and making the concrete denser, less porous, and more resistant to further cracking. The concrete heals itself, constantly, as long as seawater is present. It's alive, chemically alive, getting stronger every year. If you're thinking, why the hell aren't we using this today? Subscribe, because we're about to get into why modern concrete is actually worse than ancient Roman concrete. And comment, what ancient technology do you think we should bring back? Roman concrete, Damascus steel, Greek fire. Now, let's talk about why our bridges are falling apart. Modern concrete, Portland cement, the most widely used building material on Earth. 3 billion tons produced every year. And it's garbage compared to Roman concrete. That's not hyperbole. That's materials science. Modern concrete uses Portland cement, invented in the 1820s. The manufacturing process. Limestone and clay are heated to extremely high temperatures, around 1,450 degrees Celsius 2,642 degrees Fahrenheit, in massive kilns. This produces clinker, which is ground into fine powder. When mixed with water, it rapidly hardens through hydration reactions. It's fast, it's consistent, it's standardized. Builders can predict exactly how it will perform, but it has fatal flaws. Flaw 1, high heat production during setting. When Portland cement sets, the hydration reaction generates significant heat. In large pores, like dam foundations, this heat can cause the concrete to crack as it cools unevenly. Roman concrete sets slowly at low temperatures. No thermal stress. No cracking. Flaw 2, brittleness. Portland cement creates a relatively brittle matrix. When microcracks form, from freeze-thaw cycles, structural stress, or ground movement, they propagate quickly. Roman concrete's crystalline structure resists crack propagation. The interlocking minerals deflect cracks, preventing them from spreading. Flaw 3, permeability. Modern concrete is porous. Water penetrates it. In cold climates, this water freezes and expands, causing internal damage. In marine environments, chloride ions penetrate and corrode steel reinforcement. Roman marine concrete becomes less permeable over time as new minerals fill the pores. Flaw 4, no self-healing. When modern concrete cracks, it stays cracked. Repairs require external intervention, epoxy injections, overlays, or complete replacement. Roman concrete repairs itself, continuously, for centuries. And there's another massive problem. Portland cement production is an environmental disaster. The cement industry produces 8% of global CO2 emissions, more than the entire aviation industry. Why? Because making Portland cement requires heating limestone to 1,450 degrees Celsius. That requires enormous amounts of fossil fuel energy. Plus, the chemical reaction itself releases CO2 when limestone breaks down. For every ton of Portland cement produced, approximately 0.9 tons of CO2 are emitted. Roman concrete, made with lime burned at lower temperatures, used volcanic ash, a waste product, required far less energy, produced far fewer emissions, and lasted 20 times longer. Let's compare lifespans. Modern reinforced concrete structures, design lifespan, 50 to 100 years. Reality. Many require major repairs after 30 to 50 years. Marine structures, 20 to 50 years before significant deterioration. Constant maintenance required eventually must be demolished and replaced. Roman concrete structures, built 2,000 plus years ago. Status, many still standing, intact, functional. Marine structures, getting stronger with age. Maintenance required, minimal to none. Some still in active use today. We built worse, with better technology, with more knowledge, with advanced science. The Romans beat us with volcanic ash and lime. So let's get into the actual science. What's happening at the molecular level that makes Roman concrete so special? Research by Marie Jackson and colleagues used multiple techniques: electron microscopy, imaging concrete at nanometer scale, X-ray diffraction, identifying mineral composition, Raman spectroscopy, analyzing chemical bonds, synchrotron radiation, high-energy X-rays revealing crystal structures. What they found was remarkable. Roman marine concrete contains altobermarite, a mineral that's extremely rare in nature and exceptionally stable. It forms at temperatures of 50 to 80 degrees Celsius under pressure over long time periods. The Romans weren't creating it intentionally. They didn't know it existed, but their mixture lime, volcanic ash, seawater, and time created the perfect conditions for it to form naturally. Here's how the self-healing works. Step 1. Microcrack forms in the concrete due to stress or environmental factors. Step 2. Seawater infiltrates the crack, carrying dissolved minerals, particularly aluminum and silica. Step 3. The water reacts with the unreacted volcanic ash particles remaining in the concrete. Step 4. New crystals of altobermarite and philipsite begin growing in the crack. Step 5. These crystals fill the crack, bonding to the existing concrete matrix. Step 6. The crack is sealed. The concrete is stronger than before. This process continues indefinitely as long as water is present and there's unreacted volcanic ash in the mixture. It's not just durable, it's anti-fragile. It gets better with stress. But there's another recent discovery that changes everything. For years, scientists noticed white chunks in Roman concrete, lime clasts. They assumed these were impurities, evidence of poor mixing or low-quality lime that wasn't properly slaked. They were wrong. 2023 research published in Science Advances by MIT and Harvard researchers revealed that these lime clasts are intentional. And they're brilliant. The Romans used hot mixing, adding quicklime, calcium oxide, directly to the mix instead of pre-slaking it into lime putty. This created two things. 1. Extreme heat during mixing up to 200 degrees Celsius, which changed the chemistry and allowed different minerals to form. Point 2. Reactive lime clasts scattered throughout the concrete, small reservoirs of calcium hydroxide. When cracks form, these lime clasts get exposed to water. They dissolve, releasing calcium ions that precipitate as calcium carbonate, sealing the crack from the inside. It's not just self-healing. It's preloaded with healing agents, distributed throughout the structure. Waiting. The Romans engineered redundant self-repair mechanisms. Without knowing chemistry, without microscopes. They did it through trial, error, and genius observation. If this is blowing your mind, ancient builders out-engineering modern science, hit that like button. Your engagement helps this reach more people. And comment, should modern construction switch to Roman-style concrete? What would you be willing to sacrifice for buildings that last 2,000 years? Because there's a catch, and we need to talk about it. So the obvious question, if Roman concrete is so superior, why aren't we using it? The answer is complicated. Challenge 1. Setting time. Roman concrete took weeks to set fully. Modern construction can't wait that long. Projects have tight schedules. Contractors need concrete that's load-bearing in days, not weeks. Modern society operates on speed. Roman society operated on permanence. Challenge 2. Volcanic ash availability. The specific type of volcanic ash the Romans used, pozzolana, exists in limited quantities. Global demand for concrete is massive. There's not enough volcanic ash to replace Portland cement entirely, though modern researchers have found that fly ash, a waste product from coal power plants, can partially substitute. Challenge 3. Standardization. Roman concrete was artisanal. Each batch was slightly different. Builders adjusted mixtures based on experience and local materials. Modern construction requires standardization. Engineers need to calculate load-bearing capacity precisely. Insurance companies need predictability. Roman concrete's strength varies. That makes modern engineers nervous. But despite challenges, researchers are developing Roman-inspired concrete formulations. Seawater concrete, using seawater instead of freshwater in concrete production, combined with volcanic ash or fly ash. Self-healing concrete, incorporating bacteria or crystalline admixtures that seal cracks when water penetrates. Low-carbon alternatives, replacing some Portland cement with supplementary cementitious materials like volcanic ash, fly ash, or slag. Hot mixing techniques, deliberately creating reactive lime clasts for self-healing properties. Several pilot projects are testing these formulations. Marine structures in the Netherlands using seawater concrete. Experimental highway sections with self-healing additives. Low-carbon concrete used in some sustainable building projects. It's happening. Slowly. But it's happening. But beyond the specific chemistry, Roman concrete teaches a deeper lesson. Modern doesn't mean better. We assume progress is linear, that each generation improves on the last, that ancient people were primitive and we're advanced. Roman concrete proves that's wrong. The Romans achieved something we still haven't replicated, not because they were smarter, but because they prioritized differently. They built for permanence. We build for profit. They built for centuries. We build for decades. They built to last. We build to replace. And their structures are still standing, while ours crumble. The Pantheon Dome, still perfect after 1,900 years. The harbor at Caesarea, underwater for 2,000 years. Getting stronger. These aren't just ancient structures. They're monuments to a different philosophy of building. The Romans understood something we've forgotten. True quality reveals itself over time. You can't see the difference between Roman concrete and modern concrete in year 1 or year 10, but by year 50, year 100, the difference is obvious. Modern materials science is finally catching up to what the Romans knew intuitively. Durability matters more than speed. Natural materials can outperform synthetic ones. Self-healing systems are superior to static structures. Simplicity often beats complexity. Long-term thinking produces better results. We have better tools, more knowledge, advanced computers, sophisticated chemistry. But 2,000 years ago, Roman engineers, without any of that, built structures that shame our modern work. Maybe the secret isn't in the volcanic ash. Maybe it's not in the lime clasts or the altobermarite crystals. Maybe the secret is in the intention, the commitment to permanence, the pride in creating something that will outlast you by centuries. The Romans built for eternity. We build for quarterly earnings reports. And that's why their concrete still stands, while ours crumbles. If this changed how you think about ancient versus modern technology, subscribe to this channel. We prove that history has secrets that shame our present. Smash that like button. Every like helps this content reach more curious minds. And drop your answer to this. If you had to choose between a building that lasts 50 years built quickly, or one that lasts 2,000 years built slowly, which would you choose? Be honest. There's no wrong answer, but I want your reasoning. I'll see you in the next investigation, where we prove that ancient peoples weren't primitive. They were genius. Until then, remember, true quality doesn't age. It improves. The Romans knew that. Maybe it's time we remembered.